Hello, everyone, and welcome to the IAQG webinar for the APQP Advanced Project Planning series. This one today will be focused on the design risk analysis. I'm just going to go through a couple of tips and get started here. So we'll start right away. Just want to get through these tips, and that's just to let you know that you might want to close down as many programs you have open in the background, because that will help with any lag time issues. This is a live audio broadcast, so you are on mute. There's no dial-in number. Also, if you have questions, you can see the QA box over to your right side of your screen, and you can type in something along the way. If it's specific to a certain slide, it's good to have that slide number in that question. Helps us go back to it if we need to. And feel free to ask those questions anytime during the presentation. It's going to be a shortened start to this presentation. We're not going to go through all the details of the SCMH, the Supply Chain Management Handbook. I'll have a couple key slides and show you how to get there, where the webinars are located. But we're going to go right to the focused topic and then have more time for Q&A at the end. So this is recorded, and the presentation and the Q&A will be posted along with the recording in the SCMH. There's not going to be any certificates provided today. This isn't a training. It's more of an awareness session to allow people to ask questions, and we use those questions later to improve the guidance. If you have more than one person joining you in a conference room, appreciate you just popping in that number in the Q&A box. So it's for more than one person. Just put 2 or 50, whatever it might be, and then that gives us a better idea of the number of attendees. So today we'll just, we went through the webinar tips. We're going to go right into the topic, like I said, follow that with a Q&A session. And then at the end of the presentation, we won't be sharing them during this recording and webinar, but they will be in the presentation that's going to be posted in the SCMH. And I'll show you how to access that. Okay. And I'd like to introduce the panelists today. It's Brian Garcia from Pratt & Whitney UTC and Steve Finup from GE. So I'll let them take it from here.
Okay, thank you, Sue. Good morning, good afternoon, good evening. Welcome to our webinar. My name is Brian Garcia. I'm a 35-year veteran of the jet engine business. The past 14 years I've been with Pratt & Whitney. I've also worked 10+ years each at GE and Allied Signal, now Honeywell. I've been a structures and design engineer. I've worked in technology and product development roles. I've supported manufacturing and quality as well. So I've been working across the entire life cycle of products. I'm a Six Sigma Black Belt and Master Black Belt, and I've applied DFMEA, Design for Six Sigma, and Lean principles across the product development processes. So that's me. Steve, why don't you go ahead and introduce yourself?
Hello, everyone. My name is Steve Finup. I've been in engineering and aerospace and automotive for 23 years. For the last 18 years, my focus has been on reliability, maintainability, and safety engineering. Over my career, I've performed many different types of failure mode and effects analysis, but for today, I'm going to be focusing on design FMEAs.
All right. Thank you, Steve. All right, so we are here. This is one of the webinars of the entire family across APQP. This is the second one. We're talking about key elements of the process and the 9145 standard. Today's webinar, the primary audience are really those suppliers, those people who have design authority. However, this is also useful and can show manufacturing suppliers that have critical knowledge of process capability, how they can support design teams with optimization of design tolerances, specifications, and other requirements. Just a note, Steve and I cover a lot of information in this webinar. It is really intended to provide awareness. This is not detailed training or how-to on this subject, any of the other things we cover. A lot of this information and the expertise around it is available. A lot of it is publicly available we're really not going to cover anything that probably you haven't seen or heard of before. Also, as Sue mentioned, we will have time for questions at the end of this presentation. We wanted to take a moment to remind everyone that when you look at APQP and look at advanced product quality planning, that the word quality in APQP does not mean that this is a quality-only process or that the quality organization or function is the owner of APQP. Really, the intent here is to say that APQP applies to the entire product life cycle from the very early concept phases all the way through product sunset and retirement. And it really involves all functions of the business, I should say the business enterprise. So you can think about, programs, profit and loss centers, operations, quality, engineering, and so on. Everybody's involved in APQP. This is a team sport. Here are our objectives for today. We're going to introduce an approach with a set of methods and tools to help design responsible organizations with the APQP requirement for design risk analysis. You might also hear us say DRA, so DRA, design risk analysis. This webinar is not intended to cover the other requirements of Phase 2. We'll talk about all of that in a moment. And our basic objective is to support the continuous improvement of the design system. We want to reinforce current approaches and perhaps highlight some opportunities for new thinking and new ways of approaching the subject of design risk analysis. This is a rather detailed agenda for today. We're going to cover design risk analysis purpose. I'm also going to talk about and have a discussion of what design risk is involved and what it means for our purposes. And we're going to highlight certain methods and tools, and Steve will later cover DFMEA in some reasonable detail. A lot of these methods and tools are well established and generally recognized throughout aerospace and actually a lot of other industries. We are essentially going to be following Design for Six Sigma, or DFSS, and lean product development practices and principles. This overview is not intended to be all-inclusive. This content should really complement your organization's design system. It's not intended as a replacement or to say that, this is the right way to do it or the only way to do it. We expect that all the appropriate design processes, systems, methods, and tools will be used for design risk analysis. For example, using finite element analysis would be part of this application. Again, Steve's going to focus on the DFMEA section later on, and I'm going to cover the rest of this. So this is the You Are Here chart relative to the 5 steps of APQP. Design risk analysis is Phase 2, and this is where we're going to cover today. And note that the remaining webinar series is going to focus on the remaining elements of APQP, including PPAP. So 2 weeks from today, you will see that the process flow diagram PFMEA topics will be covered. And then November, control plan, December, measurement systems analysis, and then in January, process capability and control, and lastly, PPAP approval. This chart here shows the specific Phase 2 activities and requirements per the 9145 standard. Note that design risk analysis is also a required element of PPAP, and as I said earlier, this webinar does not cover the other requirements of Phase 2. All right, so let's get into design risk analysis and what it is. I'm going to start with, at the top, 9145's definition, and also show here a high-level description of design risk analysis. The basic objective is to ensure rigorous and thorough evaluation of design risks and also provide accurate and timely flow down of product key characteristics to the next phase of APQP. We're going to introduce thinking and tools shown on the left as we progress through this webinar. And I do want to indicate that this is a hardware-centric discussion. Software design has agile and related methods that are not in the scope of this webinar. However, the principles and concepts are generally applicable for pretty much any design and development situation. So now I'm going to talk about why it's useful and what does it look like. And there's a variety of reasons for the usefulness of DRA. The power of this is actually most evident in how we can influence design decision making. If you think about the decisions made early in the APQP process and early in the product development process, we can think about how the cost of what I'll say is poor decision making, which can be due to lack of knowledge of your design space, what you know, what you don't know, along with high levels of uncertainty and variation. This can create waste and impact your ability to provide value to your customers. We're going to talk about knowledge, uncertainty, variation in a few slides, and these are key themes throughout the webinar. For now, note that DFMEA is an obvious and probably minimum expectation for documentation output of DRA, but it does not preclude all the other related evidence and documents as you walk through design risk analysis or execute your design and development process. Steve's later going to show a simple example of how to use DFMEA for documentation of design risks identified by other means, and so you'll see a simple example later. Now, I'm going to try to answer a question which has come up since we first aired this webinar back in November of last year, and it has to do with why do we not just specify design FMEA in the 9145 standard. And so what I wanted to do here is just have us consider the entire APQP suite of methods and tools. So if you look downstream of design risk analysis and KPCs, or key product characteristics, you'll see a whole set of tools and elements that we are going to talk about in follow-up webinars. But if you consider all those methods and tools, think of that as what I will just dub process risk analysis. These emphasize important tasks and tools to enable robust execution of APQP steps 3 and 4. So as you can see here, step 3, process design and development, and step 4, product and process validation. So I'm going to ask a kind of rhetorical question. We probably would not be satisfied with only spiking out PFMEA for this entire sequence of activities in APQP. So similarly, when we looked at design risk analysis, or DFMEA, we said, you know, with this one box called design risk analysis, we want to highlight the same kind of rationale and thought process for DRA in step 2 as we are in steps 3 and 4 of APQP. And lastly, before I wrap this up here, I just want to mention that DRA is not only about phase 2 of APQP. Design risk analysis thinking, methods, and tools should really be started in the first phase of APQP, which we call planning, as shown here. So, as I said, design risk analysis is not just about DFMEA. So, on the right of this slide, under process risk analysis, I've put in some graphics of some of the key tools and methods that might be applied. And you can think of this, for those of you who are experienced in Six Sigma, DMEA, you can see this is a pretty traditional collection of those tools. The DMEA methods and tools are widely accepted, understood, and adopted across multiple industries, particularly when we come to manufacturing parts and assembling products. On the left side, the design risk analysis, we've shown a comparable set of methods and tools. And as I said earlier, you can think of this as design for Six Sigma. Interesting enough, DFSS does not have the same universal recognition as DMEA, at least not in my experience. DMEA, or DFSS, has models like DMADV, DMEDI, IDA, CDUV, and so on. And this shows the greater degree of DFSS approaches that are tailored to the uniqueness of products and their design and development systems across multiple industries. So this webinar is really about including recommendations and way to think about design risk in addition to these sampling of tools. These techniques are not intended to be exhaustive or all-inclusive. It does not represent the entire scope or gamut of an organization's design and development system. This sample, this short list, is really representing techniques to enhance the design system, as I mentioned earlier. This slide is just to highlight a couple of citations from the 9145 standard to reinforce the requirement for design risk analysis as well as the role of the DFMEA. And I do want to note that DFMEA is certainly necessary and will almost always be applied, and I could almost say 100% of the time will be used, but it's not always the only tool, as I've talked about recently. Note, too, that your customer may dictate use of DFMEA or other tools and techniques via contract flow down and other requirements. All right, so let's get into some terms and concepts. I mentioned that the power of a good design risk analysis is its ability to influence design decision making. So think about poor, inadequate decision making. A lot of times these have roots in lack of knowledge, high levels of uncertainty, and unknown knowledge about variation. The impact of poor decisions will magnify throughout the rest of the product development process, and this can potentially reduce the value received by your customers. So DRA, design risk analysis, is a pretty important step considering how early it is in the APQP life cycle and how early it is in product development. So as I go forward, I want you to consider a different perspective on design risk. So I'm going to start with some definitions of language, and I've used some of these terms earlier, but I wanted to specify them a little bit so that we can calibrate our approach to the rest of this webinar. So in the top of this slide in the upper right, there are two spaces as indicated. One is called the design space, that little blue object there in the middle. This is the place your design needs to be to satisfy your customer. The second space is knowledge space, and that's what you know today, what your organization knows. Its technology, its capabilities, its methods and tools, the proficiency and skill of your people. Ideally, your design space for your customers' requirements and expectations will be completely contained within your knowledge space. The second thing I want to add to this is probabilistic thinking. So in the middle, you can see uncertainty, which is low confidence in what you know. Variation, which is things tend to be different. It can be small variation or large variation. And finally, at the very bottom right, you might see or recognize the Taguchi loss function, which basically says the further off target you are due to variation, the greater the loss in customer and business value. And this is especially true for key characteristics, which we'll come back to later. Okay, so for my purposes in this webinar, the definition of design risk is really going to be centered around knowledge gaps. Gaps in your knowledge, what you do and don't know, and particularly what you don't know, represent risk. And that's the region where your design space and your knowledge space do not overlap. So your team's knowledge map might resemble those of earlier explorers, mariners, and cartographers, as the graphic on the right indicates. Your teams will need to explore their knowledge and design space much like those old explorers would set out to discover new lands. Now, what I want to talk about in the middle here is various combinations of what you do know and what you don't know. So first off, let's talk about the known knowns, and these are things that you know well. It's very mature technology. You're very high in the learning curve, and basically your risk here is just poor execution. Let's talk about the known unknowns, and this would be the edge of your knowledge space, the frontier of your product capabilities, regions you have not explored, but you know they're just right next to where you are. Thirdly, let's talk about the unknown unknowns. These are beyond your knowledge base, not just unexplored, but potentially not even recognized. And finally, and maybe the worst of all, the unknown knowns. This describes lost, forgotten, or discarded knowledge that would really be in the known knowns, but for some reason just has not been institutionalized. So in this context, design risk represents all of these combinations of unknowns. You can also consider these risks with terms like new, unique, or difficult. So the use of risk analysis intends to reveal these unknowns and to support mitigation activities via generation of the right knowledge in support of your design decisions. Consider, too, that good mapping and exploration may increase the likelihood of uncovering your unknown unknowns. All right, let's move on now. I'm going to step back and talk about key characteristics. So as you explore your knowledge space and design space, you're going to determine that there are important things like special requirements, critical items, and product key characteristics. These are all defined in the 9145 standard. And as you look at this chain, it shows the relationship of those items that affect the overall value proposition that you offer to your customers. So we start at the top. Things that are important to the customer are important to you. So the design and process risk analyses methods as you go through APQP help you determine what you must control to consistently provide that value to your customers. In the spirit of our discussion of knowledge unknowns, we can restate that special requirements as defined in paragraph 3.26 of the standard. These exist at the limits of the design and knowledge space. Another important thing to note here is that not everything is a key characteristic. So again, we want to use DRA to ensure objective knowledge and risk-based selection of product key characteristics. And a note that I'm emphasizing product key characteristics. Many of you are probably more familiar with process key characteristics, which are flown down through specifications, blueprints, drawings, etc. But there's two pieces to the key characteristic as defined in the 9145 standard. And more on that here. Your business and your customers, you probably have other terms with similar definitions. You know, we talk about special requirements, critical items, and key characteristics in the standard. Notice if you have automotive background, they have other terms as shown here in the second bullet. But even these are not consistent across the automotive industry. And note too that there are ongoing discussions in the 9145, the APQP industry committee meetings on other terms if they add value for aerospace. We did get some input from the IAQG, the Automotive Industry Action Group, that they had never in the automotive industry really agreed to harmonize on one definition or system for key characteristics. And their recommendation would be for us in aerospace to really collaborate and see if we can come up with a consistent set of terms in the system. All right, so I understand that language and all that can be or can create confusion, but we're going to try to level set on the terms in the 9145 standard, at least as far as these webinars go. All right, let's get into methods and tools. So I want to talk about, the design risk analysis thought process and how we got here. And again, I just want to reinforce that these are meant to complement your design system, and we want to support continuous improvement by reinforcing what you do today and how you might think and behave differently based on what you learn in this webinar and the entire series of webinars, as well as with the 9145 standard. So this slide is showing a dynamic for the DRA methodology. So the point here is that we're trying to create first an inventory of the domain of design characteristics. So we're kind of starting at the top. Secondly, we want to create a link between design characteristics and custom requirements. And I'm using the phrase design characteristics as defined in the standard in paragraph 3.8. And finally, we want to filter all these design characteristics down to the most important few, the critical few, and these would be the product key characteristics. This graphic implies a linear serial relationship, but in reality, there's going to be iterations and some back and forth within and between these activities. As I discussed earlier, we are creating knowns from unknowns. We're trying to map and visualize the knowledge and design spaces. So depending on the mix of knowns and unknowns for any given design risk analysis, this dynamic is scalable, and again, only use what is necessary and appropriate for the risks at hand. And this represents a very methodology to process risk analysis in steps 3 and 4 of APQP, and it really is talking about a design for Six Sigma type methodology. So I'm going to cover a couple of qualitative tools and then a handful of quantitative tools, and then we'll get into DFMEA. So first, the P diagram. This is a pretty common tool across many industries. In this case, I'm using it as analogous to a process SIPOC. It's intended really to create an inventory of cause and effect relationships. It helps you create transfer functions between inputs and outputs by identifying factors for your design and for your experiments and other tests and activities. And it can also support input to the DFMEA and other design risk analysis tools. So Steve's going to cover DFMEA here shortly, but from that perspective, you can think of DFMEA effects as tied to your system responses, and failure modes and causes can be tied to the list of inputs, noise, and control factors. Lastly, the P diagram can be built from block diagrams and other design depictions like schematics and so on. These sets of tools and thinking may be familiar to you, maybe not. The decision map may not be. The causal analysis, critical parameter management are techniques from Design for Six Sigma. You can think of these as analogous to a process flow map in APQP Phase 3 or as used in the DFMEA project. And like process maps to PFMEA, they provide input to DFMEA and the rest of the DRA methods. The decision map is a product-centric graphical representation of customer expectations. It shows the list and the set of relationships or transfers functions between inputs and customer expectations. And it promotes lean thinking in the product development process by allowing visualization of the creation, reuse, and flow of knowledge. So this very simple graphic on the left, the yellow boxes would depict your customer requirements. And again, these would support identification of failure effects in the DFMEA. The blue boxes are inputs. These could be design characteristics and process characteristics. The red and green dots, those icons, indicate knowledge status, green for known, red for unknown. The gray boxes depict relationships between inputs and outputs, where transfer functions should be identified and also are coded for whether you know or don't know the knowledge contained therein. The blue and gray boxes and their knowledge status provide failure modes and causes to the DFMEA. And finally, they create and visualize knowledge of the product design space. And here, we want to bring in everything we know from physics, from tests, simulations, rules of thumb, experience, customer experience, field experience, and so on. So let's talk in the next few slides about some quantitative tools. So first, I want to talk about the notion of design quality and how it relates to our understanding of knowledge and design space. So think about the dynamics of how we achieve robust design and appreciate and understand variation from earlier. So a note, variation occurs everywhere and everything. And I want to highlight that you can ignore it at your peril, or you can recognize and actually use it to your advantage and to your customer's advantage. And I pulled out from paragraph 313 for key characteristics this phrase on the slide. Variation control is necessary for fulfilling customer requirements and enhancing customer satisfaction. That phrase is applicable to process key characteristics, as many of you are probably familiar, but it's just as applicable to product key characteristics. So I wanted to highlight that. I also wanted to talk about how in many design, development, engineering systems, we typically use point-based techniques. In other words, an input has one and only value, and an output has only one value. So then we take that output value, we calculate a margin, a factor of safety, and we try to account for variation. However, calculating margin or factors of safety can hide the true impact. For example, let's say you calculate 20% margin on a key parameter. This might sound good, but say there's an underlying 5% defect rate due to unknown variation. This could exist and be unacceptable. So in a couple of slides, we're going to explore this in a simple example. The point here is that approaches unmasked variation allow you to use it. It helps you quantify product capability, much like process capability is measured by things like CP and CPK. So product capability really equates to a measure of design quality. So the benefit is that you can actually provide visibility to reducing unneeded over design margin, which actually adds to customer value and actually adds to the value in the business. And finally, it allows you to really introduce manufacturing suppliers' capabilities from their processes, which can help enhance the creation of material and dimensional requirements by a better understanding of variation. So this graphic here on the right shows that without understanding of this distribution, we're going to put in an extra margin to make sure we cover ourselves. But in reality, if we actually understood the true distribution, we can actually manage this variation, take out some of that excess margin, and come up with a better value proposition. And we'll show this again in a couple slides in an example. Lastly, let me talk about, two more tools. DOE, it's really about a disciplined and robust mechanism to execute tests, whether they're physical tests or simulations. It allows us to explore the design space, expose gaps in knowledge, create new knowledge, and make that knowledge visible. So in this chart, this gray region could represent your design space, and it might not be completely known, but as you experiment in a region as indicated by this, what looks to be a blue-gray box, you can actually map that and visualize that knowledge and actually start to understand where your optimums might be in your design space. In this example, moving to the upper left, for example, could be your local optimum. So this graphic depicts factorial-style designed experiments, but Taguchi designs, mixture designs, space filling, and other designs provide similar benefits. And finally, I want to talk about Monte Carlo simulation. This is a technique to determine the impact of variation on outputs due to variation in inputs via a simple model or a complex model or transfer function of that relationship. It directly supports calculation of risk, design quality, and product capability. It also supports decision mapping and critical parameter management. It's a great follow-up to DOE modeling and allows identification of variation drivers, which we would call product key characteristics. And this then allows you to provide improved flow down into APQP phases 3 and 4. All right, so we've added a simple example. We did not have this in last year's webinar. We wanted to use this to demonstrate some important themes in this webinar. First, how we can use DRA with probabilistic techniques to address variation risk and mitigation. Second, how we can reveal unknown knowledge. And 3, how these can be documented in the DFMEA. And I do want to note that I'm going to cover the first 2, and then Steve will include how to document other risks due to using tools like these when he gets to the DFMEA. So this is a very simple example. Let's just say we have a bracket. It supports one end of a component like a gearbox, say, and we want to understand its capability relative to steady-state maneuver loads. So we're just going to have this beam loaded in the middle. It has a length, a width, and a thickness dimension. We have material requirements for deformation and plastic yielding, as well as ultimate rupture, failure, complete breakthrough of the beam. Obviously, we want this thing to not rupture, and we also don't want it to deform too much. So we're going to examine this with a very simple model. So for those of you who have mechanical engineering, material engineering backgrounds, you might recognize the bending stress. That's less important for our discussion as to what you would do with this analysis. Typically, we would look at our design factors, the point load W, and then the 3 geometric features. We would describe their nominal values and perhaps their worst case values. Now, the way I came up with these worst case values, just for our purposes, was I took the nominal and I added or subtracted 3 standard deviations. That's done just for this example. It's not applicable in all cases, but I wanted to make a point here about comparing nominal predictions of margins, worst case prediction margins versus probabilistic predictions. So in this case, we have very easy decisions to make. If we do margins from a nominal case, we see that our beam will yield, has 8% margin and has a 26% margin for ultimate rupture. So we might declare that this is a good design. If we look at it from a worst case perspective, we'll see that we have negative margins, so that we have a bad design and we would need to do some redesign efforts to make it move back into the positive side of margins. Now, let's take a look at this from a probabilistic perspective. And in this case, a very simple Monte Carlo simulation. We're going to describe our 4 inputs with normal distributions. We're going to use the parameters as shown, and when we do that, we actually predict a 22% probability of yielding the bracket. We can also determine that the beam thickness H is the greatest contribution to this variation, and then we can use that information to mitigate our risks, which leads us to reducing variation H, and we would describe this as a product key characteristic. And notice that in the prior chart that B and L had such low impact of variation, we could make those non-key characteristics and actually allow slightly more variation in those. That allows us to balance the key characteristic needs for control versus others that don't. So when we do all that, you can see our margins are here on the left, and you can look at the probabilities of failure. From 22%, we can improve that to 9%. From yield, we can improve the ultimate stress from really low to almost non-existent. So the point of all this is to really demonstrate how we can predict and manage risk and calculate design quality, show that how just by adjusting variation, we greatly reduce that risk. Now, I will admit this is a very simple and a bit of a contrived example, but I just wanted to highlight the differences in some techniques about how we approach design, and that in reality, if you were going to optimize this, you would include the nominal dimensions as well as the variation dimensions, but this was just to make the point about variation uncertainty and expanding your knowledge. I wanted to end this section before I turn it over to Steve with a real-world example from experiences in the jet engine world. When we applied these very methods that I just highlighted on an engine critical item, we were able to substantially reduce design risk by actually spiking up the design quality, much like we did here in this example, and by identifying what were key and non-key characteristics from a very long list of design characteristics, much like I showed earlier. So what happened as a result of this, a historically tightly tolerance key characteristic was determined to have little influence on overall variation, and the tolerances were relaxed for improved producibility. The result was $250,000 of savings for one feature on one part. It demonstrated the value of design risk analysis and robust design methods to that of worst case over design and excess margin. So with that, let me conclude this section of the webinar. I'm going to turn this over to Steve for the DFMEA, and I'll come back after his section for a couple of wrap-up slides, and we will be done with the formal presentation. Steve, over to you.
Thanks, Brian. If you want to go to the next slide. So in this section, we're going to be discussing the design failure mode effects analysis, its use on design risk analysis tool, how can it be used to record the results of other design risk analysis tools, as Brian has described, the DFMEA is compared to other FMEA tools, and when it is implemented into a program. Next slide, please. So there are multiple types of FMEA tools. The most common to aerospace is the failure mode, effects, and criticality analysis, or FMEA, which is used to support the safety assessment process. The other two most well-known are the process FMEA and the design FMEA, which have their origins in the automotive industry. There are also FMEAs such as system FMEAs, software FMEAs, logistical FMEAs, and countless other processes to which the FMEA methodology can be applied. Historically, automotive does not have a functional safety assessment process similar to aerospace. Therefore, a FMECA or a safety FMEA has not been used. The automotive industry uses the DFMEA to identify and action safety concerns. Therefore, in automotive, the DFMEA does a double duty evaluating piece part physical failures and design errors. As DFMEAs are adopted into aerospace, there's a significant overlap to the FMECA process, and that's causing confusion. From my experience, when requested by a customer to perform a DFMEA, the customer expectation is a full automotive type of DFMEA, which becomes a redundant exercise to the FMECA or the safety FMEA, which really drives the confusion. The next two slides are directed towards how aerospace is clarifying that confusion. And just as a note, with the emergence of automotive complex systems and components, the automotive industry is now adopting a safety assessment process similar to aerospace. You can reference ISO 26262 if you want more information on the automotive process. So just comparing the three types that I've discussed previously, the FMECA, the existing aerospace process, addresses physical failures. It calculates a failure rate and is used to input into the system safety assessment or the fault tree analysis. As an example, an oil tube which has a physical failure, which could be a crack, caused by vibration resulting in a leak. The failure rate is assessed as X failures per million flight hours. Now, if you look on the right-hand side, the PFMEA addresses manufacturing process errors. It evaluates each for severity, occurrence, and detection relative to the manufacturing process. It calculates a risk priority number, or RPN, and defines actions to eliminate or reduce the manufacturing process risk. A relative example here is the oil tube has a manufacturing forming operation, which results in a thin wall section. That thin wall section does not withstand the vibration environment, ultimately resulting in a crack and a leak. The RPN is used to determine if an action should be taken relative to the manufacturing process. In parallel to the PFMEA, the DFMEA, as applicable to aerospace, addresses design errors. It evaluates each for severity, detection, and occurrence relative to the design process. It calculates an RPN and defines actions to eliminate or reduce the design process risk. Using the same example, the oil tube wall thickness in the design process may be selected, which does not withstand the vibration environment. In operation, that could result in a crack and a leak. The RPN will determine if an action should be taken relative to the manufacturing process. Next slide, please. Looking at the three FMEAs together, if you look at the center box, the functional hazard assessment, or FHA, defines the system criticality. The FMECA evaluates design contributions to the criticality, considering one failure at a time. The fault tree analysis considers combinations of failures, which will lead to the failure conditions defined in the FHA. The criticality should inform the severity ranking in the DFMEA and the PFMEA. However, it's possible that the DFMEA and PFMEA may identify new criticality considerations, which should be fed back into the functional safety assessment process. You should also note that failure effects can be leveraged between the three analyses. Next slide. Basic assumptions of the DFMEA. The DFMEA will address the design intent and assume the design will be manufactured to this intent. Design for assembly and design for manufacturing should be considered as part of the DFMEA. However, the DFMEA should not rely on manufacturing process controls to overcome potential design weaknesses. However, it does take the technical and physical limits of manufacturing assembly process into consideration. In talking about timing, DFMEAs are most value added if started early to identify and address design risks. The DFMEA should be iterated on as the design matures. And the DFMEA is a living document, which means we should continue to update it as the design updates over the entire product life cycle. The DFMEA is a great tool for capturing lessons learned, and then when a new project or product design is started, you can use that existing DFMEA as an input into your design process. Thus, the cycle time becomes shorter between every product cycle. Next slide. The DFMEA should include various things such as lessons learned from in-service manufacturing previous designs, DRA risks identified, environmental risks, sources of variation, manufacturing producibility risks. And then as you go through your design process, you will perform various analysis. And these analyses should be, such as stress and thermal analysis, should be considered as part of the DFMEA controls. However, these may identify risks not previously considered and should be incorporated back into the DFMEA as new risks. So the DFMEA, what does it look like? In the AS 9145 committee, we have been working on a standardized DFMEA template. We've been working between IAQG and AESQ to define what that is with member representatives from multiple aerospace organizations. It will soon be released into the SCMH as a standard template with associated examples. Note that the DFMEA is a spreadsheet type exercise. It can be completed in tools such as Excel or with specialized software programs. Now looking at the form, the template contains a header section which captures all the relevant information about the DFMEA event itself. So that's the items highlighted in blue. And it also contains an analysis section which assesses and actions design risk. The template that we will be releasing will contain instructions to how to capture design risk analysis information within the DFMEA format. Note the example shown here is the example that Brian previously described with the bracket. Now the left side of the form is the risk identification portion up through the potential causes of failure column. Best practice is to work left side of the form first, identifying all the risk items. Then starting with the severity or SEV column as it's shown here, the DFMEA is structured to prioritize risk and assign actions to eliminate risk. So once you've done the left-hand side where you've defined risks, now you're going to be working the right-hand side, addressing how to action each one of those risks. The current prevention controls are an organizational or industrial standard practice which will be implemented on this program, which will mitigate the risk at some level. The OCC or occurrence is a ranking which will define the applicability of the prevention controls to mitigate the risks. Next slide, please. Continuing with the analysis section, current detection controls considers if the design error occurs despite the preventative controls, what is the ability of the design process to detect the failure mode? The DET or detection is a ranking which will define the applicability of the planned process to detect the failure mode. This is a time-based criteria. The earlier in the design process to detect the failure mode, the better. The RPN is the risk priority number, which equals the severity times the occurrence times the detection. The RPN is used to prioritize risks. If two RPN numbers are equal, the severity times occurrence column can be used to define further priorities. Actions are then assigned to lower the RPN, and action results and the new RPN are documented. A best practice is to not use RPN thresholds as a means to define actions. You don't want to automatically discount any RPNs that, for example, are below 100 as a threshold. Those could be something that the team really should be investigating. Next slide. DFMEAs can be performed at many different design levels. System FMEA is a specific type of DFMEA analyzing combinations of components for risk relative to the requirements and the interfaces. A key point here is that DFMEAs can be performed at different levels of the assembly. When this is done, be aware of a possible relation between the causes and failure modes between the levels. Next slide. Now this is a little bit of an eye chart, but it's meant to define how requirements, critical items, and key characteristics will flow through the DFMEA to the PFMEA to the process flow diagram. So in the upper left, you have basically your voice of the customer, your customer requirements, performance data, things like that, which will then step through and go through the blue box and the orangish box there to identify if an item is a special requirement, a critical item, or a key characteristic. Ultimately, those should all flow into the design FMEA. The design FMEA evaluates the CIs and KCs as part of risk mitigation, and if possible, drives design changes which eliminates or reduces the risk and the associated CI or KC. It should be noted that the DFMEA may also identify new CIs and KCs to add to the list. When the DFMEA is completed, the remaining CIs and KCs are transferred to the PFMEA. The PFMEA then evaluates the CIs and KCs and, if possible, drives process changes which to eliminate or reduce the risk and the associated CI or KC. The PFMEA may also identify new CIs or KCs to add to the list, and these things may be transferred back to the DFMEA for evaluation. Any remaining CIs or KCs are transferred to the process control plan, and the process control plan defines how the CIs and KCs are controlled in the manufacturing process. For any future design or process changes, the DFMEA and PFMEA should be reviewed to ensure that the original CI and KC determination are not violated or that new CIs or KCs are not introduced. Note that a requirement of 9145 is to ensure traceabilities of the CIs and KCs through the various analyses. This can be accomplished by defining a CI or KC master list and use a common numbering scheme. So that really briefly covers the description of DFMEA. I'll turn it back over to Brian.
All right, thank you, Steve. So let's wrap this up. I've got basically one slide, and we'll conclude, and then we'll move on to the Q&A. So I wanted to return to this definition of design risk, which I covered earlier. Look at the takeaway in the bottom slide. I believe we really look and rigorously and disciplined way look for knowledge gaps, and we close those gaps using design risk analysis. We'll be able to really create improvements in our design quality and then increase the likelihood of downstream success in the rest of APQP and product realization and the overall performance of our products and systems to the benefit of our customers and end users. So again, just to emphasize that knowledge gaps are risks. These are the combinations of what your organization does and does not know, and that your product development teams will need to explore these spaces to uncover the unknowns using design risk analysis and then support mitigation activities by creating the right knowledge, the right time to support design decisions. So at the beginning, we said that our objective was to support the continuous improvement of the design system, reinforce current approaches, and highlight opportunities for perhaps new thinking and other methods and tools. I hope you've gained an appreciation for these reasons and the purpose of design risk analysis to the benefit of you, your organization, your customers, and the entire industry. So thank you for your time and attention, and I will end on the schedule for the remaining webinars. And I think we now go to Q&A.
Yes, we do. I'm just going to quickly introduce myself. I'm Susan Parsons, and I work with the IAQG. I support the product and supply chain strategy stream. And the product that we have is the Supply Chain Management Handbook, or at least that's one of them. And so I'm just going to go over a couple of slides. As you see on the front of you, this is the webinar screen, one before the webinar listing. They're all getting scheduled. The links will go out. We post them in the SCMH on the announcement page, but you'll also, if you're a registered user of the SCMH, which is you will be sent the invitation as the links are available. We usually do that a couple weeks before, 2 weeks to a month before the webinar. We'll send that invitation out. Okay. And just so maybe there's a few people that you've invited into the conference rooms or are on the phone for the first time and haven't seen some of the other webinars, I have just put up here a quick link to the IAQG.org site. And if you do a /SCMH, you'll get right onto that page. I answered a couple questions where people were asking, would the presentations be available? Would we be sharing the recording? If you look there where it's circled, there's a little webinar tab. In that webinar tab, this presentation and the past recording is actually already posted there. So we will update that with a newer presentation where a few things have been added and this recording from today. So again, I said there's some backup slides. You will see them posted within the presentation when it gets onto that site. And that will give you some more details on how to register and get into the site. Next. So now we're just going to start some questions. I'm not getting too many questions, so you can take your time in responding to the first couple while people have a chance to jot their questions in the question box. This first one, is the design FMEA required for items that will go into a commercial aircraft cabin but are not installed items? For example, additional cushions, blankets that will be delivered under a certificate of conformity. They went on to say, specifically items that may be in use during flight but must be stowed away during TTL, so taxi, takeoff and landing. More specifically, items whose possible use during TTL impacts an installed parts ETSO during TTL. So the first part of that question, is a design FMEA required for items that will go into a commercial aircraft but are not installed items?
So I guess to address the first part of that question, it sort of depends on what the customer requirements are. A DFMEA is not a requirement per 9145, but your customer may require a DFMEA from you. So it's sort of depending on what the customer requirement will be for those items. Ultimately, I think the takeaway from this webinar would be it is a good idea to perform a design risk analysis and potentially document those items in the DFMEA.
Slides 41 and 42, any discussion on updating the DFMEA template to align with the new automotive action priority number versus RPN?
We've had those discussions. Currently, we are not planning to align with that. There's still some variation, I guess, within the automotive industry on how they're going to apply that new handbook. And it sounds like there is an update of the J1739 standard coming out, which may provide some more clarification on that. But so currently, we are not planning to align with the AIAG VDA handbook, but we are monitoring it.
Okay. What would be the DRA PPAP expectation of a supplier without design authority?
Yeah, I think typically if you do not have design responsibility, that the DRA element, the DFMEA aspects would not be applicable. You would receive, as one of your inputs, you should get some summary of the design risks, be it they coming from the DFMEA or from a DRA.
Okay. And I think the person went on to say, example, a printed circuit board manufacturer serving aerospace customers receives designs from their customer and will conduct design checks, but don't have design control. How might they satisfy the DRA requirement of the PPAP?
Yeah, so again, they wouldn't necessarily, it depends on, I can't say for sure if they have any true design responsibility other than from an incoming receipt, if they're, building the, I think it's circuit board to specifications received from a customer, then presumably the design risk analysis and the DFMEA were done by that customer or that provider. The opportunity would be to use the rest of APQP from phases 3 onwards, not just from your own benefit for manufacturability and so on, but also to provide feedback to the aforementioned design party in terms of perhaps increased knowledge about how to improve their design and make it easier for you as the producer.
Yeah, a smart design authority person or organization will involve their manufacturing suppliers in that design risk assessment type activity, just so they can be cognizant of what any manufacturing limits may be or any restrictions. AS 9145 does allow for tailoring. So that if there's a specific phase that's not applicable to your organization, then, for example, if you're strictly a manufacturing organization, you do not do any design, then phase 2 would not apply, and then that part of the PPAP would not apply as well.
And again, for slide 40, DFMEA can be used to identify KC, but not necessarily a correlation between risk of incorporating a design weakness, RPN score, and effect on performance of varying that same characteristic KC candidate. I think it's a statement. Any discussion?
Could you repeat that? I'm sorry.
Yeah, yeah,
Sure.
please repeat that.
So they were talking about slide 40. Yeah, and it said the DFMEA can be used to identify KCs. That's the first statement.
Yes.
But not necessarily a correlation between risk of incorporating a design weakness, RPN score, and the effect on performance of varying that same characteristic, KC candidate.
From the first half of the statement, sounds correct. I'm not sure the second half, from the way it's worded, it should actually help identify potential risk from a design perspective, whether it's a manufacturing risk or a performance in the hands of the customer, risk to performance.
Okay. I think that was more of a statement than a question, but if that person has a question, you can type it in now and we'll read that and go back over it.
Yeah, I just wanted to highlight the second to last bullet on this slide, where source of variations will impact product performance or customer satisfaction are included in DRA and DFMEA activities. I think that addresses the statement, but
okay.
If not, please clarify for us. Thank you.
Okay, and then actually there is another question that says who should be involved in the creation of a DFMEA?
That one's actually pretty easy. I mean, it's as Steve alluded to just a moment ago, it should be an integrated approach. It should include certainly the designers and the product, those people involved in creating the design, but it should include all the other stakeholders that are involved in the upstream and downstream processes applicable to make sure that all the pertinent risks to the enterprise and to the customer are represented. Steve, I don't know if you want to add to that.
No, that's exactly right. It is a team activity. It should not be done in isolation. It shouldn't be one person sitting in a room doing it. It really is a team activity.
Yeah, and as Steve highlighted, this should be an ongoing cycle of learning and capturing knowledge, So the DFMEA is a great tool for institutional knowledge management in terms of, as Steve talked about earlier, about capturing what you know, updating it with things later, and then just continuing that life cycle across multiple product design efforts across the organization so that it is indeed a living document, and the next design team, the design team after that can go back to the starting point and make sure that what you do know does not become your unknown knowns, that you don't forget things as an organization.
Next question, statement leading to a question. I agree that knowledge space and design space exploration and understanding is vital to DRA practice. This is strongly connected with the set-based design / set-based concurrent engineering practice. What role does quality engineers play in DRA currently?
So first, I appreciate the recognition of the connection of set-based principles and methods to my discussion here, so thank you for that. And as far as quality engineering, again, going back to the earlier answer for DFMEA, quality engineer, depending on their exact role, they should be providing current and historical performance back to the design risk analysis, bringing that knowledge back in so that it is not overlooked, forgotten in the process of executing design risk analysis.
Yeah, it sort of depends on how the organization is set up. So in some cases, the quality organization is more of a facilitator of DRA, DFMEA type activities, and in other cases, they're more involved with providing information, what Brian said.
Okay. While we ask the next few questions, answer the next few questions, could you move the slides down to, I think it's around 50, where it shows how to access the SCMH? Apparently, some people have been sending requests on how to access it and how to, or where to find the webinars. I think it's the one before. So right there. If people are still asking questions about how to access the SCMH, right there you go to iaqg.org/SCMH. There'll be a quick pop-up that says register. You can actually see it at the top of the top of that picture where it says log out. There should say a log in or register when you first come to that page. A couple quick questions, and then you'll be able to access the webinars and recordings and presentations right there under that webinar tab. Okay. Next question. I would like to know who are the stakeholders for FMECA, FMECA?
So it's a lot of the same individuals that for the design FMEA, but the FMECA is really very safety focused. So you'll have your safety organization driving that as be a stakeholder as well as your design organizations.
Oh, go ahead. Is there more to add?
Nope, that was it. Sorry.
Okay. Is DOE exercise required for aero material qualification?
Design experimentation, unless your customer or some other regulatory agency spikes it out, I wouldn't say it's required. I would suggest that it would be very useful and highly recommended to help understand it. But again, it would go to the specific cases of the material qualification in hand.
Okay. This is a good question. Where could the touch points or interfaces be with the ARP 4754 and ARP 4761, which engineers are more familiar with?
So this slide here actually touches on that, so this is a good slide. So the middle boxes there are really your 4761 activity. So you have your functional hazard assessment, your FMEA, your system safety assessment with fault tree analysis. And so this is a very simplified view of how the DFMEA and the PFMEA align with that process. An organization may actually start a DFMEA very early on and should start a DFMEA very early on, which may highlight some criticalities that the functional hazard assessment as it's being developed has not fully fleshed out yet. So there's definitely a feedback process that goes through these three types of analyses.
Is there any guidance in APQP for how to rate the three values that are multiplied into an RPN? Are there scales for each one somewhere?
Yeah, so for each one, you will have a ranking table. So for severity, we're defining a ranking table that goes from 1 to 10, same for occurrence and same for detection. So that'll be part of the template that we'll be producing. And if you could go, Brian, back to the SCMH slide we were on before.
Yep.
Slide 50 or so.
Yep.
So we got the webinar tab circled there. If you go to the one to the left of that, plan and manage tab 7, that's where you will see all the current APQP content as far as templates and forms. So when you will see a DFMEA template on there right now. That's the one that we're updating. We're also updating PFMEAs, process flow diagrams, control plans, other templates to put on there, as well as defining additional templates. So that'll be the tab that you'll go to for finding those templates. And I had someone ask me a private question about where the templates are going to be published. So if you want to see the current, go to that tab. Here within about a month, maybe 2 months at the latest, you will see the updated template put there as well.
And that leads right into our next question. It seems that we have a lot from novices to experts joining us on our conversations and with questions. And this person nicely stated, just started a career in purchasing department in an aviation OEM. They're a startup and they have many suppliers and want APQP process from them. But he admits he has no idea on APQP and how he can be more effective. So we just pointed out that not only with this webinar series, which I believe there's 8, they're currently all posted with recordings on the webinar site. We are doing them again. So this series that we're going through right now, this is the second in the series, we'll be posting them as well. But we, as you just pointed out in section 7, that tab 7, you have 7.2, which is APQP, and it has the main APQP manual with all of the templates and supporting guidance in there as well. So I would take a look at that and attend the rest of the series, and you'll become a lot better, a lot more knowledgeable on the APQP process. If you do not have design authority, the make-to-print manufacturer still requires severity levels in order to complete the PFMEA. True statement? I think that's what they're asking.
That is a true statement.
Yes, true statement.
And then they added DRIs. So, yeah.
Yep.
KC is an attribute or feature whose variation, but could we determine a KC from severity weight? If yes, what is the criteria?
So yes, typically any kind of FMEA, the common and best practice is to evaluate severity in and of itself, regardless of probability of occurrence or detectability, just to make sure that things that particularly are in aerospace, high severity tends to relate to safety, but also could relate to significant degradation of performance. So those, just severity alone, can be used as a method of identifying a product key characteristic or a process key characteristic.
And there may even be examples where you will have a lower RPN number, but it contains a high severity number. And in those instances, you will still evaluate that line item from a severity perspective alone. So we do consider severity in isolation and in combination with occurrence and detection.
Next one is a statement followed by a question. In my experience, in some companies, the design risk analysis is often superficial. Normally, the company has not decision map available because not specialized in certain fields or has not enough information about the interrelation with other systems. Which level of in-depth is appropriate, in your opinion, for review during the audit process?
I'm going to maybe look at this slide. The graphic on the right really, in one way, kind of helps peel back the onion of design risk analysis and the role of the general FMEA, DFMEA cycles, starting at system level effects. Steve earlier talked about FMECAs and the functional hazard assessments relative to safety. The system FMEA is a good way to look at the overall system that you provide to a customer, and in this case, the effects are how it won't perform in the hands of your customers, and then you can peel back to almost like going down the work breakdown structure or the bill of material structure from systems to assemblies and sub-assemblies and components and subcomponents down to parts and even features and dimensions. So if you're talking about, I think the question was around auditing, it certainly helps to start at the top around where the system activities are done, and also looking at this chart.
Do you think that special requirements could be considered as a design goal?
Yeah, let me just go back and reread the definition, but it certainly sounds like they would be or could be. Those requirements identified by the customer determined by the organization which have high risks of not being achieved, that are at the limit of the industry's capability, or requirements determined by the organization to be at the limit of its technical or process capabilities. So yeah, a lot of what we do in aerospace is, you know, continually pushing the envelope, if you will, and so special requirements can most certainly be a system goal, whether it's for your own company or in conjunction with your customers.
How do you assess RPN score, example occurrence, for innovation designs which there is little or no historical data?
Well,
So one of the things one of the things we're doing, I'm part of a ASQ committee that's creating guidance on DFMEAs right now, and that'll be published, again, probably within the next 3 to 4 months. But one of the things that I mentioned previously is how we separate out the FMECA from the DFMEA and what they address. And what we're really focusing on the DFMEA is looking at design error, so the potential for a design error to occur. From a occurrence standpoint, it's no longer looking at past designs, but it's looking at what preventative controls are in place right now that may prevent a design error. And if you have less preventative controls, then your occurrence rank will be higher. If you have a very robust preventative control system in place, then your occurrence ranking will be lower.
Yeah, and another way to address that, whether you're in brand new knowledge space, if you will, or even in an area where you might have very limited sample size to do tests, which is the case in some of our products, is the use of simulation and even making a best estimate at the probabilities or distributions of inputs related to outputs, as we discussed in Monte Carlo simulation. That's another way you can start, and even though you don't know anything about the probability distributions, you can start with very simple, basic assumptions and then see where that analysis leads you in terms of overall sensitivities and impact to overall output variation.
Yeah, I think overall the occurrence ranking is looking at what do you have in place for your project to identify those design errors as they are identified, I guess. So if it's a new technology, if it's leading edge type stuff, you may not have things in place, and that's really where the analysis and the test comes in, which gets more into the detection side of the score. So if you have a high occurrence, it's not ideal, but if you have a very robust analysis that's been correlated with the test data, that detection rating may be low as well, and therefore lower your overall RPN.
This may be along the same line. When we refer to variation, does that include variation regarding the monitoring of variation for KC within the defined tolerance?
So yes, I mean, measurement system variation, which is obviously, well, maybe not, but is a topic of the measurement system analysis webinar coming up, is certainly a source of variation that should be considered as well when it comes to things like monitoring and detection.
Yeah, we mentioned before that the DFMEA should include manufacturing processes which may be at the limit of their capability. So measurement systems analysis is definitely part of that. If your measurement systems are not going to be sufficient to really understand the variation within those measurements, that should be considered as part of your DFMEA.
Is DRA the preferred method for identifying KCs, or can RPN scores from DFMEA be used also?
Simple answer is yes. DRA is the broader umbrella of which DFMEA is one technique that can be used, should be used. This example here shows how other analytical tools assessing design risk captured and were documented as a line item within the DFMEA, which was the purpose of the example we're showing here on slide 41 and 42. So you can make that connection if you want to use the DFMEA as your ultimate documentation knowledge tool, then you can connect everything else you do within the DFMEA. If your customer has your DFMEA as a requirement, then everything is in there regardless of whether it was done with a DFMEA analysis or whether it was done with other tools and methods.
Following is a statement. The critical elements of a design should be reflected in severity rating and reflected within the RPN.
Correct.
Okay. RPNs may be used to prioritize risk for action to reduce overall risk as part of their continuous improvement activity.
Correct. And as Steve mentioned, I want to remind that the RPNs are useful from a relative perspective. For example, I've seen rules where RPNs greater than 200 or 300 should take action, and RPNs lower than that would not. However, that is not a good practice, and unfortunately some people will work their scores to make sure that nothing exceeds a prescribed threshold. So it's really intended to be a relative risk assessment. As we mentioned earlier, severity in and of itself is also a technique used to define mitigating actions because of the high consequence and impact to customers. Also, severity times occurrence, severity times detectability, those are also good ways of interpreting a DFMEA. So RPN is obviously useful, but it's not the only way to assess relative risk and mitigating actions.
Random failure modes should be considered in the DFMEA? That was a question. So should random failure modes be considered in the DFMEA?
Yes.
Okay. Failure modes caused by a lack of control, in parentheses, manufacturing, should be analyzed in the DFMEA? That's a question.
Well, that should be part of your PFMEA exercise, looking at the control within your manufacturing process. So the PFMEA would be looking at process risk, manufacturing process risk, and the ability to control your variables.
Available, applicable for all the different types of products?
Could you repeat that? I didn't catch the first part.
Well, the way it's worded, it says, does the grids available are applicable for all the different types of products? I think they're asking if the grids available are applicable.
So it sounds like the FMEA scores and templates, yes, they are applicable everywhere.
Okay. A product could be broken down into many functions and or subsystems. Any ideas on how to select the ones a P diagram would be critical to support DRA?
So you could look at, if you look at it from a relative knowledge perspective, is the particular component, subassembly, and how you break down your product structure, are you in known territory, and this is something that's very known and mature within your organization, or is it totally brand new and outside of your design space, and that can help you prioritize your activities and some of these methods and tools?
Is the DFMCA applicable to expandable space launch systems and satellites?
Of course. Yeah.
Okay.
Yeah.
Do DFMEA and PFMEA are not focused on safety as PFMEA or as FMECA does? It's a question, though.
So within aerospace, we have the functional hazard assessment, the system safety assessment, FMECA process is a standard. Automotive, until recently, did not have that, so they used DFMEA as part of their system safety assessment. Within the DFMEA and PFMEA, though, you definitely consider the safety aspect from the criticality and effects perspective.
So to wrap, I think it was a follow-on to that launch system and satellite, specifically to low quantity or single item production through full project cycles for space applications?
I would say, well, certainly, if you're in the one output in a very long streaks of time, these things might even be more important just because you basically have one shot at getting it right, and pardon the pun. So clearly, yes, the intent of the entire APQP process, DRA, and everything else we've talked about is applicable up and down and across the entire industry, the entire aerospace and defense industry.
Okay. And I think that takes us to the end. I think there was only maybe two more questions. I'll do it real quick. Why not expand the design risk analysis block in the 9145 as it has been done for process risk analysis for PFMEA and MSA?
Yeah, that's a good question, and I think that's been something that the 9145 sub-team has been evaluating over this past year. So it's probably something we'll continue to explore.
Okay. And I think since it's the last question, we might as well ask it. Could we synthesize that a CI having sufficient effect on the product realization, but if variation, the CI will be a KC?
Sounds like yes. If I understood that the critical item has variation which could impact the overall performance and other requirements, then it could potentially be defined as a product key characteristic.
Okay. I think I want to thank you guys. It brings us to the bottom of the hour, so we will just say thank you, and we appreciate you attending the webinar today. Any last words from Brian or Stephen?
Thank you for your attention, and I hope this has given you some food for thought and will help you and us in our ongoing efforts to improve how we as an industry operate.
Okay.
Yeah, thank you very much. And I guess, Sue, I don't know if you mentioned the survey, if that's available.
It's not available yet, but there will be an APQP survey coming up shortly, and we'll send that out to everyone. Probably talk about it at the next APQP webinar.
Excellent. Thank you, everyone.
All right.
Thank you.
Thank you. Have a good day.